Welcome. We're on our Chapter 7 exam practice page 1 and number 1. We've learned to estimate unknown population parameters using best point estimates as well as confidence interval estimates, and here we'll focus on symbols. So the best point estimate, if we're trying to estimate an unknown population mean, mu, our best point estimate would be the result from our sample, so that would be the known sample mean, and that's x bar. All right, our best point estimate for an unknown population proportion, that would be P. So if we rely on a sample to estimate it, our best point estimate is the sample proportion P hat. And then finally, the best point estimate, if we don't have data from the population and we don't know our population standard deviation, sigma, that looks a little weird, sigma, our best point estimate is the sample standard deviation. All right, so the next questions involve alpha. So I just wanted to throw a picture up here quickly. So I just have the picture for z-scores. So this center area, this unshaded area would represent your confidence level. I'll just write confidence percent. Alpha would be the area in the tails. And in each tail then would be an area of alpha over 2. So eventually when we look for a z-score with that subscript alpha over 2, that tells us we're looking for the z-score. So the area to the right of it is alpha over 2. All right, and if that were t, alpha over 2, so t instead, it's still indicating alpha over 2 is to the right of that value. All right, so let's just focus on alpha here for a bit. All right, so let's find the value of alpha. That would be the area in the tails that corresponds to a 91% confidence level. So alpha is 1 minus your confidence level. So working in decimal, 1 minus 0.91, that would be 0.09. And I'll just write it as a percent as well, 9%. So if 91% of the graph is in the middle, 9% is in the tails. All right, so number 3, what if we want to know the value of alpha over 2, the area in each tail, corresponding to a 70% confidence level? So we'll start with alpha. So alpha, 1 minus the confidence level. So in this case, 1 minus 0.70 will be 0.30. So 70% in the middle leaves 30% in the tails. There's alpha. And then we want to know how much is in each tail individually. So we take alpha and divide that by 2. That will be 0.15. And I'll just write that in percent as well. So there'd be 15% in each tail. So 70% in the middle, and then 15% in each tail. All right, and then we'll go on and find actually the value here, z, alpha over 2. So a couple ways we can do this. Let me go through the alpha method here first. So alpha, 1 minus your confidence level. So 1 minus 0.92 is 0.08. We'll just stay in decimal now. Alpha over 2 will be 0.08 divided by 2. That's 0.04. So if we're looking for z alpha over 2, that is the notation z subscript 0.04. We want to remember here area to the right of the z-score is alpha over 2. But if we want to use our inverse norm function on our calculator, we need the area left of that z-score. So that's why we take 1 minus our alpha over 2 value. And that's 0.96. All right, so we can find z alpha over 2 by using inverse norm for normal. And then whatever we get for our 1 minus alpha over 2 value. So in this case, inverse norm, 0.96. Okay, so we'll go to our distributions. Inverse norm, 0.96. And the directions indicate 2 decimal places, so that's 1.75. All right, your other option there, if you would like, is to use, I call it a shortcut for that process. And that would be using your Z interval, where we enter sigma equaling 1, x bar equals 0, and n equals 1. So let's just check that on the calculator. So stat, and then you're going over to tests, and the number 7 there, your Z interval. You do want to make sure the calculator input says statistics, and then sigma 1, x bar 0, n 1. Enter your confidence level, 0.92, and calculate. And that positive value is your Z alpha over 2. All right, the third method would be to refer to a table, and we could look if 92% is available. So I'm going to come over to the T table in a second, and I'll show you that 92% is not a confidence level on that table. So for number 4, you've got 2 choices: inverse norm, 1 minus alpha over 2, or use that shortcut. And now let's switch to the T distribution. And here, we're either going to reference the T table, or if available, you can use your inverse T function. All right, so let's start with degrees of freedom. So every T distribution has an associated degrees of freedom, and that formula is n minus 1. So they have n 35, so 35 minus 1 gives us 34 degrees of freedom. All right, so let me just go table lookup here first. So you're going to go to our T table and look for 95% confident, degrees of freedom 34. Okay, so just going to circle some things here in a different color. All right, so up there at the top, confidence interval. So 95% confidence interval. This T table gives you the T values. And we want to go down to degrees of freedom 34. All right, so coming across there to my, make sure I get it right, the 95% column, that is your T alpha over 2 value. So I'm just going to mention here that 95% confident, if we were looking for the Z score, because a T distribution approaches, becomes the Z distribution as our degrees of freedom increases, the Z score for 95% confident would be 1.96. So Z scores are at the bottom of your T table, but we want that value right now, the T. So 2.032. All right, sorry, scrolling all over the place. 2.032. All right, so if you would like to find that value on the calculator rather than the table, then you'll need T alpha over 2. So if you have an inverse T function, it will be 1 minus alpha over 2 comma, and the degrees of freedom. All right, so inverse T. So I need 1 minus alpha over 2. So I'll just do that quickly here. So alpha 1 minus 0.95 is 0.05. Alpha over 2 will be 0.025. And 1 minus that value of alpha over 2 will be 0.975. So we can inverse, oops, I was going to write inverse t twice. We're going to inverse t for t distribution, 0.975, comma 34. So we'll just verify here that I did that correctly. It's to see if we still get 2.032. So back to your distributions. And again, some of you won't have inverse t, but if you do, 0.975, comma 34. And yes, 2.032, rounding to 3 decimal places. So use the table, or if you have inverse t and you prefer, you can use that as well. All right, so these are called critical values that we're finding, and we'll do one more table lookup for the chi-square values, left and right, that create an 80% confidence interval when a sample size is 15. All right, so here I do have everybody do a table lookup. So we'll start with degrees of freedom. So like the t distribution, each chi-square distribution has an associated degrees of freedom, in this case 14. And alpha, 1 minus our confidence level. And then I need alpha divided by 2. So we take our alpha divided by 2.10. And then the complement of that, 1 minus what you get for alpha over 2, and that will be 0.90. Okay, so we're going to go to our chi-square table. Just going to make a note here that this column gives the chi-square value on the right, and this column, 1 minus alpha over 2, so that column will give you chi-square left. All right, so let's go to our table. Scroll down here a little bit. Okay, so at the top of the table, 0.10 and degrees of freedom 14. So that value, 21.064, is chi-square right. So I drew this line down the center of our table because the values on the right side of your table will always be your chi-square right values. All right, versus looking up the 1 minus alpha over 2 value, 0.90 is what we got there. So I'm just going to point here. So that was my value for alpha over 2. And this one is my value for 1 minus alpha over 2. And that value on the left side of the table will be your chi-square left value. So 7.790. So I'm just going to scroll to the bottom of the table for a moment. So we're just learning to read the chi-square table. And again, it's the area to the right of the chi-square that the table is giving. So that's why this chi-square right is this column alpha over 2. All right, so let's write those. So let's see if I can remember that, 7.790. So that's chi-square left. So chi-square left will always be smaller than chi-square right, because on the number line there, we would have chi-square to the left of chi-square right. All right, so chi-square right is 21.064. And later in the exam practice, you'll be drawing a graph, and that might help you see that better as well. All right, let's wrap it up here, actually looking at confidence intervals. All right, so they tell you that you have a confidence interval for a population mean, and it's given as 18 plus or minus 2. So that's our point estimate plus or minus the margin of error. And we're going to switch it to the other form. So let's go ahead and just document the given information. So 18 would be the sample mean, and then plus or minus 2, so that's your margin of error. All right, and I'll show a little work over here. So the lower limit, we would take 18 and subtract 2, that would be 16. And the upper limit of the confidence interval, we take the point estimate 18 and add 2, and that will bring us to 20. So on my graph here, lower limit 16, upper limit 20. So this form, we could have changed it equivalently to this form. So that would be lower limit. And then the parameter we're estimating would be the population mean, so mu. And the upper limit there, 20. All right, so the idea again is we would know the sample mean because we collected sample data, and we're trying to say what we believe is true about the actual population mean. If we collected data from an entire population, we believe that that value is between 16 and 20 with a certain level of confidence. All right, so let's do one where the confidence interval is for a proportion. All right, so the math here for the lower limit and upper limit is essentially the same. We're just now focusing on estimating a different parameter. So for the lower limit, we take the 0.72 and subtract the margin of error. I just wrote that incorrectly, sorry. 0.72 minus 0.03. So that will be 0.69. And then upper limit, 0.72 plus margin of error, 0.03. That would bring me up to 0.75. All right, so P hat, the point estimate is 0.72. And our margin of error, that distance from the point estimate to the upper and lower limit, is the 0.03. And that brought us down to a lower limit of 0.69 and an upper limit of 0.75. All right, so this form, we can equivalently write that information as, so 0.69 less than, and then the parameter in this case, we're estimating population proportion is P. I just wrote 6.2, I'm so sorry, 0.69. I don't know what's going on in my head. 0.69 less than P, the population proportion we would believe is somewhere between 0.69 and 0.75. All right, so just the recap here on symbols. So X bar is the point estimate for mu. This is our confidence interval estimate. All right, P hat is the point estimate for P, and that's our confidence interval for that population proportion P. All right, there you have it. That is our page 1.